Hi, we're the Humic acid sub-team. My name is Matt.
My name is Vanessa.
And I'm Carolyn.
So some background on our research and how our research pertains to alkaline as a whole is that in natural water sources such as groundwater and surface water, natural organic matter is present, and humic acid constitutes most of this natural organic matter. And if humic acid is present when water is treated with, let's say, chlorine during chlorination, it can create several acids which can lead to harmful effects when you consume the water. For instance, it could increase the risk of cancer. And so another downfall of humic acid is that it can coat the coagulant particles and making flocculation and sedimentation less effective because it's harder for blankets to form.
So in last year's research, what we wanted to do is to find the optimal coagulant dosage for the humic acid concentration of 5 milligrams per liter and 10 milligrams per liter. And for 5 milligrams per liter, the optimal coagulant dosage was 1.6 milligrams per liter to 1.8 milligrams per liter. And for the 10 milligrams per liter humic acid, the optimal coagulant dosage was 1.3 milligrams per liter. Now, we wanted to develop a mathematical model, but the problem is that even with the huge change in the concentration from 5 to 10, the resulting optimal coagulant dosage was very little, from 1.6 to 1.3.
So from previous semester of research, we find out it's not very promising to find the optimal coagulant dosage for different humic acid concentrations. And for this semester, we also have a new instrument, which is a UV-spectrometer. So that will help us to find out what's the effluent absorbance and what's accordingly what's the effluent concentration for our experiment. So we want to basically investigate the humic acid effluent concentration as time change or as the coagulant dosage changes. But before we start all those experiments, we also have to conduct 3 preliminary tests because the absorbance we measure will only be the total absorbance, and we want to separate them into the humic acid absorbance and the clay absorbance because we only want to know the humic acid concentrations. So for the experimental setup, the bench is pretty much like last semester. We have 4 pumps for clay, water, humic acid, and coagulant. And we have 2 thermometers for influent and effluent. We have the flocculator, and we also have the spectrophotometer on the very right to measure the effluent absorbance.
And so, as you guys know from our symposium presentation, when we tried to first use the original spectrophotometer that we wanted to use, there were issues with the absorbance readings in that absorbance readings came up as negative, which is physically impossible. Absorbance readings should be between 0 and 1. So what we did, we first ran a preliminary test using the UV-1600 PC spectrophotometer in the design lab. And we took 3 different samples of humic acid, 5, 10, and 15 milligrams per liter. And we measured the absorbance at 254 nanometers, which is the established absorbance wavelength that you can find in literature, and we measured the absorbance using the spectrophotometer. And on the right side of the slide, you can see our graph, which plots the data points we collected, and we can see that there is a linear relationship which follows Beer's law, so we expect this result. And Beer's law states that absorbance should be proportional to concentration, which with the slope of E times L. And so our big conclusion we can take from this is that our procedure for using spectrophotometry to measure concentration of humic acid will work, and that we can continue to run experiments using the spectrophotometer.
So like Matt said, we did face some problems with the spectrophotometer, and we spent a lot of time on troubleshooting. And the problem we find out in the end is we did actually use the right size of the cuvette, which is the small bottle in the spectrophotometer. So after we have changed that, all the problem actually got solved, and we got reason number for the absorbances. So then we start our second test for the clay and water. So for the test, we basically ran the tap water through the spectrophotometer, and we measured the corresponding absorbances, and we plot the data for the graph as a graph, and you could see there's a linear relationship between the absorbances and the clay turbidity. That means in the future, if we know the clay turbidity, we could basically calculate the clay absorbances based on the linear relationship we developed from this graph. And that's a very good result for us in the future experiment. So for the third test, we still want to test the humic acid concentration and absorbances by the QView spectrophotometer we will use for our experiment. So we still ran the humic acid solution with a known concentration, and we measured the absorbances, and we still get a linear relationship, which means we re-verify the Beer's law like the first experiment, and that means for the future experiment, if we know the humic acid absorbances, we could just calculate the humic acid concentration based on the relationship we could obtain from this graph. And there's also another result we find from this experiment, which is when we ran the humic acid solution through the turbidity meter, we find the turbidity of the humic acid is pretty low. That means when we measure the effluent turbidity, we could just consider that turbidity as a clay turbidity as a contribution of the humic acid particle for the turbidity is very small.
So for the last two tests that we did, we understand the relationship between turbidity and the absorbance for clay and the concentration of humic acid and the absorbance of humic acid. So for our future work, what we want to do is make a recycled experiment where the system would run on its own and we wouldn't have introduced tap water from the pump. We would have a set of 4 liters of water in the system and we would run it through. And then we would add increments of humic acid. So first we would add increments from a pipette so that the whole concentration in the system of humic acid would be 5 milligrams per liter. And we already know the absorbance of humic acid at this concentration. And then we will add the clay at a certain turbidity to the system. And from this, we would see the absorbance of the entire system on the spectrophotometer. And because we already know the absorbance of these 2 separate factors, what we want to see is if we could just do a simple addition of these 2 factors, and that's what it would result on the spectrophotometer. And we would continue to do this for different turbidities and different concentrations of known humic acid. And the thing about this whole new experiment is that we don't know the interactions between these factors, the clay and the humic acid. So we would like to see some interesting things happen to these things when we do the experiment. And also the good thing about this is that when we try to do this in a non-recycled experiment, we had to wait for the flock blankets to form in like 7 hours. So we had to wait a long time, and there are many complications with this. And with this whole new system, we would not have to wait that long. All we have to do is wait for the entire system to run for maybe half an hour, and we will get the corresponding results and see if there is any relationship between these 2 absorbances and their ultimate final absorbance.
And thanks for watching our presentation. And if you have any question, you can send us email or give a post on GitHub, and we will answer your question.
Here are our appendix slides. This is our Percoda setup if anyone's interested. And then this is our Python code example for one of our graphs.
So if you're interested in our Percoda data and you want to, let's say, rerun our experiments, you can do so, or you can just see how we plot it.